Hi everyone. Today in this lecture we are going to derive the element stiffness matrix of a constant strain triangle using the potential energy approach. The potential energy of the system pi is given by this formula: half integral over the area sigma transpose into epsilon into the thickness minus integral over the area displacement into the body force thickness dA integral over the length displacement into thickness dl minus summation into ut pi. I indicates the point of application of a point load pi, and since it is a two-dimensional body, pi is given by px py at I transpose. The summation in I gives the potential energy due to all the points. Using the triangulation, the total potential energy can be written as pi equals to triangulation. Initially in the first lecture we saw we were given a body and we divided it into smaller triangles. So this is the triangulation I am referring to. So it is given by summation E, that means there are a number of elements. Now sigma transpose, we know that sigma is D, that is a material property matrix, into epsilon. So sigma transpose will be epsilon transpose into D. D is a constant matrix which depends upon the material properties. So substituting for sigma transpose, or we could also write it as pi equals to summation of all the elements UE, and the rest of the terms are unaltered. So what I'm doing in this equation is that I am defining the first term as the element strain energy, denoted by capital U suffix E. So we know that UE equals to half integral epsilon T D epsilon into thickness dA, and this is the strain energy of the element. Now let us derive the element stiffness using the above equation. So we know that the strain is given by B into Q, where B is the strain displacement matrix and Q is the displacement vector. So substituting for this, we get half integral, and from this equation we'll get epsilon transpose will be Q transpose into B transpose. So we have Q transpose, B transpose, D, B, Q into the thickness dA. Taking the element thickness Te as constant over the element, and remembering that all the terms in D and B matrices are constant, we can write that UE equals to half Q transpose B transpose D B. T is now written as TE, so I have rearranged the terms into integral dA into Q. We know that the integral of dA has to be equal to A E. Okay, so we are replacing by AE, and this is the area of the element. So we have the strain energy UE equals to half Q transpose into the thickness TE into the area AE B transpose D B Q, or this can be written as half Q transpose KE into Q. So this term here TE into AE B transpose D into B is replaced by KE, and KE is the element stiffness matrix, which is TE AE B transpose D into B. Now this D here will depend upon whether it is a plane stress case or a plane strain case. This small ke that we have found out here, this is the element stiffness matrix. As we know, when we want to find out the solution to a problem, what we will do is we will combine all the element stiffness matrix to get the global stiffness matrix. Okay, so the strain energy can be given by summation E half Q transpose KE into Q. Okay, so here what we are doing is we are adding up all the element stiffness matrices to form the global stiffness matrix. This can be given as half. So now here capital Q stands for the global displacement vector, and capital K is the global stiffness matrix. So this is how we will find out the stiffness matrix for a CST. In the next lecture, we shall see how to find out the force terms for a CST. Thank you.